Good afternoon, everyone, and welcome to the 2019 Jump into STEM webinar series. Jump into STEM is sponsored by the U.S. Department of Energy's Office of Energy Efficiency and Renewable Energy's Building Technology Office with support from the Oak Ridge National Lab, or ORNL, and the National Renewable Energy Lab, or NREL. So today's webinar is on our challenge related to designing a healthier and energy-efficient air distribution system. Melissa Lapsa from ORNL, and I'm very pleased to have Grant Wheeler from NREL presenting as well today. Our vision with Jump into STEM is to inspire the next generation of building scientists by focusing on supporting creative ideation and diversity in the building science field. The Jump into STEM program provides a gateway or on-ramp for undergraduate and graduate students to experience the research and career possibilities of studying building science. Our intent is to attract students from diverse majors and diverse backgrounds. So our project team is managed by Mary Hubbard from the U.S. Department of Energy, Dr. Kim Trenbath from NREL, as well as Jahi Simba from NREL, myself, and Dr. Yunjin Bae from ORNL. We're pleased that we have a very large professor team that helps to promote and communicate the program with their students and others. The Jump into STEM challenges are open to any student enrolled in a U.S. college or university. Our professor team from Georgia Tech, Hampton University, University of Tennessee, Colorado School of Mines, Southern University, Clark Atlanta University, University of Alabama, North Carolina A&T State University, and Tennessee State University promote the Jump into STEM at their school, and many offer it in their classrooms this fall for a student grade. We also have an advisory panel from ORNL, NREL, NSF, and ORAL that provides guidance to us on our outreach and the program as a whole. With Jump into STEM, our goals emphasize cultivating diversity of thought by underscoring the importance of interdisciplinary teams inclusive of women and minorities. Jump into STEM works with university and college professors from a variety of disciplines to support creative building science challenges that can be integrated with coursework curricula. Jump into STEM's network includes leveraging public-private partnerships with industry partners and STEM organizations to support annual student challenges and events. With this slide, you can see a quick snapshot on how the Jump into STEM student competition works. Eligible students can compete for up to 4 paid internships at either ORNL or NREL. You can go to jump.ideascale.com to view the eligibility requirements and the full schedule. Click on how it works at the top of the homepage to view a step-by-step process on eligibility, building a team, ideation, and idea submission requirements. Also on the top navigation bar is a schedule for the Jump into STEM 2019-2020 competitions. Eligible students can participate in any of the 3 concurrent online challenges running now through to November 15th. These challenges are supported by online webinar series designed to provide insights on industry practices, market issues, and other supporting resources to help students build and generate their idea solutions. After the 3 challenges close on November 15th, the Jump into STEM team will run a judging process to select finalists to compete on January 31st, 2020 in a final event competition hosted either at NREL in Colorado or ORNL in Tennessee. During this final event competition, judges will award the 2020 Jump into STEM internship winners. So now I want to just give you a brief overview of our 3 concurrent challenges that are running right now until November 15th. The first 2019-2020 Jump into STEM challenge topic is focused on smart sensors and controls for residential buildings. Participating competitors interested in this challenge topic should develop a unique application that uses sensor data in residential buildings for the purpose of reducing energy, maintaining or improving occupant comfort, and/or to provide better responsiveness to the electric grid. Strong ideas will present a proposed approach, identify the sensor data, and how the data will be used. The idea should also discuss the anticipated impact and a tech-to-market plan for the application. The second Jump into STEM challenge topic is to design a healthier and energy-efficient air distribution system for a small commercial building setting using your local climate zone. And Grant will talk more about this in his presentation. Strong Ideas will identify a novel system for the selected climate zone and will present implementation of the solution in a hypothetical or existing building. Solutions should articulate the expected impact from the design system and also include a tech-to-market plan. Again, there's much more information about each of these challenges on our website at jump.ideascale.com. The third Jump into STEM challenge topic this year is focused on pushing the envelope with innovative wall retrofit designs. Students are challenged to design a residential wall retrofit product or system that can address replacement or supplement of current leaky and unhealthy walls. Strong Ideas will identify how the wall retrofit will work and will be inclusive of details on how to address the issues of moisture and air tightness. Additionally, the IDEA solution should address one or more of the following issues: low indoor air quality, high energy costs, and/or high retrofit costs. Like the other Jump into STEM challenge topics, the IDEA solution should include a tech-to-market plan. So these are some images of our final event from last year, which was held in conjunction with the Solar Decathlon at NREL in Colorado. And this final event enabled our finalists to pitch their ideas in person and network with other students, professors, industry stakeholders, and lab staff. So the results were that we did have 3 winners who were awarded internships for this past summer. 2 were awarded 10-week internships paid internships at NREL and 1 at ORNL. I won't read through all of this, and again, these slides will be available on the challenge website later this week, but I wanted to give you a flavor for what each of these students worked on in the building science field during their 10-week internships. And all 3 had a very great experience and enjoyed working at the laboratories. There was Cade Lawson and Sarah Tinsley. And finally, Carl Woodard. So with that, I will introduce Grant Wheeler from NREL. Very pleased that he's going to be, actually that title is incorrect. He's going to be talking about designing a healthier and energy efficient air distribution system. So Grant Wheeler is a research engineer in the Building Energy Science Group at NREL in Golden, Colorado. His expertise is in evaluation of HVAC&R systems in the lab and field, development of advanced controls for HVAC&R systems, and determination of building load flexibility using HVAC&R systems. So with that, I will stop sharing my screen so that Grant can show his slides.
Thanks, Melissa, for the introduction. Let's go ahead and get started. All right, let's see. Can people see my screen? Hope we're good.
Yes, yes, I think we're good. It's in, it's not in slide, there it is. There you go.
All right. Perfect. Well, as Melissa said, my name is Grant Wheeler. I work as a research engineer in the Building Energy Systems Group in National Renewable Energy Laboratory in Golden, Colorado. Awesome place to come visit, so we hope you get that chance. And I'm here to talk about a healthier and more efficient air distribution system. So in terms of the challenge, there's kind of 3 topics I'm really going to highlight today, but there are 5 just to go through. But the main one is just talking about proper ventilation for buildings, what kind of indoor air quality hazards there might be that you might need to think about, and then number 4, which is just reduce the energy consumption compared to current systems. And in general, what I would like to say is that I'm providing some resources so that you can go and research and actually find this information for yourself, and hopefully provide some ideas as well as to where you can kind of think outside the box compared to current systems and current buildings today. So first off, why indoor air quality? One of the points made is that we spend a lot of time in buildings. One survey said 87% of our time is spent in a building. And this is not something that is just happening now. We have had a history of being in a building. That is because we are using it for protection from weather, from sun, and from other environmental considerations, such as safety, right? Problem is, when you get into a building, you can actually concentrate pollutants. And here is just an example of some of the things that we've been dealing with throughout history. So looking at first, just fire, right? From that fire, you have combustion, and you have all of these byproducts. Carbon dioxide, carbon monoxide, nitrous dioxide. These are all gases that are actually very harmful if breathed in. Another thing to think about from just combustion is ash particles. People with asthma, people that have other health conditions are going to be negatively affected by particles in your air. Looking at the ground or the environment that's underneath us and what we're trying to protect from sometimes. You have dust, you have mold that's caused by humidity getting into your building, and you have radon. Radon's one that I never thought about when I was in college, but now that I'm a homeowner, Colorado has a high amount of radon, which is an actual naturally apparent radioactive material, and it can actually cause harm to humans. This is something that we actually try to mitigate currently in buildings. Finally, two other options to look at are airborne disease. Think about a hospital. If someone is sick and is coughing and sending all those viruses or bacteria into the air, how does our air distribution system manage that and prevent the spread of disease? One I always like to think about that we don't talk about sometimes is odor. Odor, right? You have a gym, you have all of these people running in their treadmill, and you don't necessarily want to smell that in the next room. You don't want to be in your lecture classroom and be smelling that. So odor is also an important consideration. And odor is the one I would say that is least considered. I think that is often something that doesn't get accounted for necessarily in today's culture. So on to one solution, which is just bringing outside air into your building, right? The common saying is the fresh air will do you good. What do I mean by that? Well, first, what you're trying to do is take the pollutants that are concentrating in your building and you're trying to dilute them by bringing in outside air. This is really important to think about, though. It assumes that outside air is cleaner. There are definitely areas, if you're next to a congested highway, you might not want to actually bring outside air in. That might not be the solution that you should look for. Also, another thing to consider is when outside air is extreme, meaning it's either very high temperature or low temperature or has a lot of water or not enough in the actual air itself, you're going to need to condition it because occupants need to be comfortable. So go back to the Middle East, right? 125 degrees outside. If you just bring that outside air into the building, you're going to have very uncomfortable occupants in that case. I'm going to talk a little bit more about the picture down at the left, but this is just an example for now of an actual building on the NREL campus that uses a certain type of ventilation strategy, pulling from the outside air and using that to both cool the building and to ventilate as well. And today I want to talk about ASHRAE Standard 62.1, which is ventilation for acceptable indoor air quality. I think this is going to be a very good resource for this challenge, and I encourage anyone who has the ability to grab this standard to go ahead and look at it. One thing just to mention about ASHRAE, first off, what is it? It's the American Society of Heating, Refrigerating, and Air Conditioning Engineers. And 62.1 specifically talks about minimum and recommended outdoor airflow rates, as well as alternative methods to ensure acceptable indoor air quality. As a college student, you actually have a chance to be involved in ASHRAE for a much reduced price and potentially get this for free. So please talk to your professors about figuring out how to get this standard and get a hold of it because it's going to provide a lot of useful information. Another point about this ASHRAE Standard 62.1 is that it's adopted by a majority of states for commercial buildings. So this is something that's commonly out there. I would say this is your baseline. You're trying to compare. You would want to look at this as kind of what are you comparing to and how are you trying to improve compared to ASHRAE Standard 62.1. Going into just kind of what ASHRAE Standard provides, it provides three different methods for quantifying how much ventilation you need for a commercial building. First one is ventilation rate method. That's been in use since 1971 with just minor changes. Another one is indoor air quality method, and then finally natural ventilation method. We're going to go through all three of these. First, the ventilation rate method. The ASHRAE standard separates ventilation based on people and the indoor environment, meaning kind of the square footage. And in this table, I've just provided some examples. So you have a correctional cell, meaning a jail or a prison. You can see in the second column the outdoor airflow rate per person. So that ranges from 5 CFM, cubic feet per minute, up to 20 cubic feet per minute. The third column is the area outdoor air rate, meaning per square footage, how much cubic foot per meter should you provide per minute. And that ranges from 0.06 up to 0.18 in this case. The important point to think about here is that what ASHRAE is recognizing here is there are different pollutants or different sources of pollutants. You have pollutants from humans, from people coming in and adding carbon dioxide to the air, or adding, airborne disease like we talked about, or odor. You also have building materials that are adding pollutants to the air as well. One example is formaldehyde. You can have actually formaldehyde coming from your materials that are in your envelope. You can also think about things that we put in the environment to make things smell better. So actually one that I was very interested in is air fresheners. I think that that's probably a pretty good idea. Well, it happens that actually can add some harmful chemicals and some byproducts that you might want to prevent. So that is kind of an example from the area-based that in a building that you might want to manage. Another thing that ASHRAE 62.1 does that's useful is it provides kind of a default occupant density. And this is kind of a suggested amount of people per 1,000 square foot. This is a tough one. I want to say that, if you look as an example, you go down to the gym and see 7 people per 1,000 square foot, there is no way that is happening as a maximum value. And so this table, this last column, is one that you want to be pay careful attention to, because it's going to definitely affect your ventilation rate. Go through with just kind of a simple example just to look at this ventilation rate method. I picked the game arcades as my building, and I looked at a 1,000 square foot arcade. I assumed the default occupant density, and then right below you can see I just separated out the ventilation based on people and the ventilation based on area. So you have about an even split of amount of air you need based on the people and amount of air based on the area, and that total ventilation is around 330 cubic feet per minute. I want to talk about what that cost is in terms of ventilation, though, because that's one thing that I really want to get across. If you were using the solution of bringing in outside air, you are going to have to be able to condition it, and that's going to cost energy. So in this example, a very simple example, I just assumed dry outside air at 95 degrees, and we were trying to bring that outside air down to 72 degrees. You can see some other examples of assumptions I looked at as well. I set a coefficient, a COP of 4, some specific heat values, and the density as well. And I separated this out again to look at area-based ventilation and people-based ventilation. What you see is about 600 watts. Not that much, someone would say. But I go back to the point. Was this 600 watts ever needed? Why did we spend the 600 watts? This is only because we decided to bring outside air to reduce the issues that come from indoor air contaminants. Another thing to think about is people versus area. In this case, it's roughly split in half. But one thing to be thinking about is, let's say you're looking at a very high density area. How high is that wattage going to go? How much power are you going to have to provide to actually look at a conference room, for example, which maybe will have 100 people in it or even more? So something to think about is that the cost to bring in outside air can become very significant when looking at all the factors. Finally, one I did not bring in here in this simple example is bringing in humidity into an environment. This is one that can be a little bit more difficult to show in a quick and simple example, but one thing I want people to consider is that air conditioning needs to remove humidity to create a comfortable environment, and that costs a significant amount of energy. So a couple things to think about. One is just reducing your temperature from outdoor air if you're in the summer. The other is to reduce the humidity. And then in heating, it's just to increase that temperature. The indoor air quality method was introduced kind of later on in, I think in the 1980s or 1990s. And this was kind of a more generic method of just saying, identify all the sources of pollutants, identify their concentrations, and then figure out how you're going to prove that the method you provide is going to actually reduce those pollutants. And this is a method I would suggest to spend some time thinking about, because this is something where you can get creative and think outside the box. Instead of looking at just bringing outside air, how can we reduce carbon dioxide to the concentration limits provided by OSHA? How can we look at carbon monoxide and make sure that the EPA regulations are followed? These are just examples, and again, I did put a reference here at the end of the slides just to talk about this is all provided in ASHRAE 62.1 in an appendix. There are other sources to be able to find this information, but again, a really good resource is this standard. And then finally, the natural ventilation method. I like to think about this as the open window method. And what it basically is saying is you need to be able to prove that you can provide the same amount of ventilation that you would have calculated from the above methods just by opening windows. And in the case of the National Renewable Energy Laboratory, we have a building called the Research Support Facility. We use natural ventilation in between 68 and 75 degrees Fahrenheit for our offices. And this is actually showing you how we do that. So we have windows on the south and windows on the north side, and those open up. They are automatically actuated based on temperature to provide this ventilation. So in this case, between 68 and 75, we are providing a comfortable condition, because that's within the comfort range for humans, and we are also providing the actual ventilation that you would need. This is, for all intents and purposes, energy-free. All we had to do was use actuators to open up the windows. This does not, however, work when you are above 75 degrees. Going back to the Middle East, if it's really humid and hot outside, this is not a good method. We will have very unhappy occupants, me being one of them. I will not come to work if it is 80 degrees or above in my office. Same with extremely cold. I will not be comfortable if it is freezing in my office, and you'll have a lot of other issues besides that. Wow, way quicker. Anyway, so final thoughts. What did I want to try to talk about here? One option is to bring outside air into the building. Key assumption here is that your outside air is less polluted. And ASHRAE 62.1 actually talks about this, some suggestions when you're thinking about that. Another key point is that it costs energy when your temperature or humidity is extreme. And then finally, think outside the box. I love to think about other situations or other environments that we're in that don't have an outside air that they can bring in. So think about a submarine. How does a submarine that is staying underwater for 6 months at a time managing pollutants that occur from both the area and people? How do planes handle outside air and ventilation? These are areas that you can go and look, and they will provide you examples that can potentially help you figure out a good solution. Finally, this ASHRAE standard 62.1 is a very common standard that is used across a lot of different states, and it's a good baseline. It's a good place to start. As I mentioned, it's based on square footage and people count. Giving you a hint, though, about a couple of the issues that we see in the field is that most people are not accounted for in a building. It's very difficult to understand how many people are in a particular building, and then based on that, how much ventilation you should provide. So one thing to look at is potentially figuring out, based on the count of people and in real time, what your ventilation rate should be. There is a whole area of industry that are working on this specific category. With that, I think I'm done and ready for any questions if there are. We're going to be looking at the chat to see if anyone wants to type any questions.
Yes, great. Thank you, Grant. That was excellent. So I have posted a message that anyone can type in any questions that they may have, or let us know that they have a question in the chat box, and then we can open up your audio line and you can ask myself or Grant directly. We'll give everyone a couple minutes here. While we're waiting, I'll just review some of the deadlines and information on our Jump into STEM challenges. The deadline is November 15th, so that's just 5 weeks away to submit your ideas online. And you first need to register on the website at jump.ideascale.com and form your team. So we need teams of 2 to 5 students with different degrees, different backgrounds, architecture and engineering, for example. And then you can go into, once you register on the website, you can go into the 3 different challenges and start reviewing the material, and you can view the webinars that are presented. If you're not able to capture them live, you can go back in and see those. You can ask any questions by sending an email to jump@ornl.gov. And you can find a lot of information on our website about the challenges. If you have questions, please let us know, and you're welcome to type in any questions now or let us know through the chat feature of Blue Jeans if you have a question, and we can open up your line. Give it just maybe one more minute here. Don't see any questions. I've covered things very well, Grant. Okay, well, with that, we will then end the webinar, and we look forward to your questions or your ideas that you submit on the website. Thank you very much for participating today, and Grant, thank you so much for your excellent presentation.
Thanks, everyone.